We're talking about affine structure from motion. Let's get back to it. Before we can actually derive the algorithm for structure from motion, for affine structure from motion, we need to understand what the affine space and affine geometry are. Okay. We already talked about what an affine space is and what affine geometry are in general terms. So, for example, we stated that affine geometry is what is left behind after eliminating all ability to measure length, area, and angles from Euclidean geometry, right? However, we also showed that the ratio of distances, the ratio of angles, the ratio of areas is preserved under a affine geometry or affine transformations. What this means is that if I do an affine projection, and maybe I'll show you, let me show you a slide here. So what this means is that if this is the same drawings I drew on the board the other day, but you know, these are computer generated, so they'll look a little nicer. So what this means is that if I start here, right, this is my space, and now I apply an affine transformation to that space, right, to that set of points, say points A, B, C, and I apply an affine transformation, then I obtain this new space, right? And these two spaces are affine equivalent because there's an affine transformation between these two, right? Now, in Euclidean geometry, right? In Euclidean geometry, if I have an object, say like this, right? All I can do in Euclidean geometry is I can translate this, and I can rotate this, maybe even rotate it in 3D, right? But that's it. It's what's called a rigid transformation, right? But in affine transformations, other things are allowed, right? So for example, I could draw, I don't have a pen, but I could draw an ellipse here, right? Yeah? So imagine an imaginary ellipse, okay? Because I don't have a pen. Anyone, can I borrow a pen? Oh, there we go. Excellent. So thank you. All right. Thank you. Not the most beautiful ellipse, but an ellipse nonetheless, okay? Now, in Euclidean geometry, if I translate this ellipse, still the same ellipse, right? You agree? If I rotate it, nothing is happening, right? It's the same ellipse. Now, in affine geometry, because I can do projections like this, right? If I rotate this or I transform this in a way that I project it now onto another plane here, right? So the original plane stays fixed, okay? But now with this fix, I rotate this other plane, and I do a orthographic projection from one to another. That's an affine projection, okay? An affine transformation. Now I can rotate this ellipse up to a point where from this plane, once I project on this plane, this ellipse is going to be a circle. This ellipse is going to start decreasing in length, right? And up to a point, the length is going to be the same as the height, meaning it's a circle. Whoops. So in affine geometry, ellipses and circles are not different things. They're one and the same thing, right? All ellipses are affine equivalent. There's no difference between them. But in Euclidean geometry, all ellipses are different. If I change this a little bit, the ratio of height to width, I have a different ellipse, not in affine geometry. In fact, one way that we will not talk about, but that is very useful to find solutions, Euclidean solutions within affine spaces, is by making sure that ellipses and circles are different. Okay? And we know that that only occurs in Euclidean geometry. In Euclidean geometry, a circle and an ellipse are two different things. But in affine geometry, they are not. Okay? Okay, so that's what an affine transformation does. Now, as you can see, this distance here, right, from A to B, has now been transformed to this other distance, which is shorter than this one, right? So obviously, distances are not preserved. That's why I can convert an ellipse into a circle, because distances are not preserved. So the width of the ellipse is decreased with a projection. However, that distance is reduced by the same ratio or factor than this one or this one. Okay? So if I do a ratio of the distance from AB over BC and AB, BC here, then that factor cancels out, which means that the ratio of distances is maintained, and the same applies to angles and areas. And if I have two parallel lines, it doesn't matter what I do, right? So if I have my plane that I had here, right, and I drew two parallel lines here, it doesn't matter how much I move this with respect to another plane, they're still parallel in the projection, right? I cannot make them non-parallel. For that, I need to somehow deform the space, right? Bend the space. And affine geometry does not allow for bending the space, okay? Only rotating. Now, if you want to see what an object looks under affine projection, this is really easy to do. Take a picture of whatever object you want, okay? So take your camera, your cell phone, and take a picture of an object right here. And now visualize this image that you've taken on a computer screen, like this one, right? A projection, okay? Now this is perspective projection. That's what we've covered before, right? I go from a pinhole camera, assuming I have pinhole camera, but good approximation, and I get my perspective projection or projective projection right here, okay? Now, you take your camera again, you place yourself at an angle, don't be frontally, obviously, otherwise it would be completely orthographic and will not do anything. Now you put yourself at an angle, and you take a picture of that picture. And what's this? This is an affine transformation now, because you're going from this 2D representation, right, and that plane, to where you are, which is your camera image plane, right, which is at an angle. And that gives you that affine transformation. And now visualize the second image in the screen and see how it looks, right? And it will look deformed, because in Euclidean geometry, which is what we like to work with, it looks deformed. But in affine geometry, they are one and the same thing, okay? So in affine geometry, in fact, I can show you one more here. These three shapes that I have drawn here, is simple MATLAB code. I think it's like 2 lines of code. You draw a number of points, and you apply an affine transformation to them. And these three objects are exactly the same under affine or in affine geometry. They cannot be distinguished in the same way that this object and that object rotated are the same in Euclidean geometry. There's no difference between this and this, because there's only a rotation between them, and we've seen that all that does is change the coordinate system, right? It rotates the coordinate system. This is the same for affine geometry. These three objects are indistinguishable. Again, this is called the affine equivalent. Okay. All right, so let's see how we can more formally define this. So more generally or formally, affine spaces are given or defined by a set of points. Let's call them capital X, and a vector space, let's call it X vector. Okay. Now, X, for example, could be, I don't know, the real space of 2 dimensions, and the space of vectors could be the same thing. Now, every vector, let's call it U in our vector space, X vector, has an associated application, let's call it phi U, from my set of points X to my set of points X. Okay? Such that for every pair, let's say PQ, okay, 2 points, there is a unique U that maps P onto or to Q. Let's see what that means. Now again, my vectors U are drawn from my vector space X vector, okay? And let's assume for simplicity that we are in the real space of 2 dimensions. So I am here. This is my X, capital X, which is defined by the real space of 2 dimensions, okay? And I have a point P right here. This is one of the elements of X, capital X, right? Okay. And now I select this U, and I apply this U to P, for example, by adding U to P, right? That's an application. So I'm going to add U to P, and that's going to give me a Q. So you see, for this application, this function, there is a unique U such that P plus U gives me a unique individual Q. If I change U, I change Q. If I change Q, I change U, right? It's just one way. That's what this means. That's all this means. Now remember that we have called this the PQ vector, right? And in our generic case, the PQ vector is nothing else than Q minus P, right? Same thing. That's what we've been using. Now, there is always a vector O that, when applied to any point P, gives me the same point P, right? And that's the origin, right? Or 0, 0, 0, 0, 0, 0 vector. That also means, right? You could also rewrite this by saying that if I apply a my transformation with the vector u onto my origin, or my O vector, or O point now it would be, in that case, then that would have to give me a unique point P, right? Now my point Q here, my element Q, is nothing else than P plus PQ, right? Correct? P plus PQ gives me Q. Yes? Okay. Now, I could have written this, if you prefer, as OQ vector, right? Remember that? And in that case, I write my OP vector plus my PQ vector, right? These two notations that we have been using are interchangeable, right? And we've covered this in detail before. However, if I use this notation right here, this is independent of my origin, right? Doesn't matter where my origin is, that equation holds, right? So it's independent of the selection of an origin. All right, so let's consider 3 points, A0, A1, and A2. So let these 3 points be non-collinear. Okay, so for example, how about this one, say this one, and this one here. So I'm going to call these A0, A1, and A2, right? You agree these are 3 non-collinear points, right? Now, let's assume also that, so we have each of these points, let's say that they are defined in 3 dimensions, okay? But if they are coplanar, as I draw them here, they define a 2-dimensional plane, right? Okay. Now, in fact, any 3 points is going to define a 2-dimensional plane, right? By definition. Now, let's select one of them as our origin. And obviously, for simplicity, why don't I say this one is O, right? The origin, because it's already called AO, so I might as well. And now I'm going to define 2 vectors from O to A1 and from O to A2, right? So this is A1, AO to A1 and AO to A2 vectors. So AO to A1 vector, and this is AO to A2 vector. Let me call these U1 and U2. Now, what I have here, I have this plane, right? So remember, I'm in 3D, and this is a 2D plane. Let's call it pi as always. This plane pi is defined by the origin, which is A0, right? And it's defined by a set of vectors, in our case, U1 and U2, right? Which are A0, A1 vector, A0, A2 vector. Now, this O plus capital U, that defines my affine space, okay? So I can say that that defines my space O plus every U, or U sub I if you prefer, with Ui in U. Okay? And that's how we define an affine space. Now, note that in the Euclidean space, I would have the exact same definition as I had here, except that I have to add 2 additional constraints, right? One of them is that U1 and U2 have to be orthogonal, very good, to each other, right? And the other one is that they have to have norm 1. And that's what's going to maintain the angles, right? Because if I impose orthogonality between U1 and U2, then all angles are preserved. I cannot break this apart. And the fact that the norm of these vectors has to be unitary, that makes it possible to measure distances, length. Okay? But here, note that in the affine space, I might have as well selected, instead of A1 here and A2 here, I could have selected A1 and say, I don't know, A2 prime right here, right? In which case, then, I'd have U2 equals this A0, A2 prime vector, right? And that will still define the 2-dimensional space, right? Okay, so I have more ways of defining the affine space. Now, how am I going to then represent any new point? Let me go back to this one. So I have, this is U1 and this is U2. How am I now going to define any point P in that plane pi? Okay, so I want to find a way to describing P, a point on pi. Okay. To do that, I'm going to use something that's called the barycentric coordinates. And what that says is that I'm going to select AJ, whichever J I have used for my origin, okay? AJ, it could be A0, it could be A1, it doesn't matter, right? One of them. And then I'm going to add to the origin all the coefficients of every other vector ui, right? So I'm going to have coefficients alpha I times ui. And I'm going to add this for I from 0 to whatever I have, say m, with I different than j, obviously. I cannot reuse j. Now, ui is nothing else than ai minus aj, right? So I can write it like this as well. Or if you want, you can also simplify this to the sum from 0 to m of alpha I and ai. They're all one and the same. And this is how I'm going to define any point P. Okay? Make sense? Now, alpha 1, alpha 2, these are my coefficients, right? So these ones here are my coefficients that I have. And that's the same thing that we had in the Euclidean space. Remember, in the Euclidean space, I had if I have a point P in three-dimensional space, which is equal to x, y, and z, we said, well, in reality, I should write x times I, the basis vector I, plus y times j, the basis vector j, plus z times k, the basis vector k. But because we know what I, j, and k are, we just write x, y, and z. That's the same thing. These are the coefficients x, y, and z now are called alphas, right? Alpha 1, alpha 2, alpha 3, right? And the vectors I, j, k now are given by ai minus aj, right? Which are these vectors that we have defined here. But they no longer have to be orthonormal to each other. Okay. So as you can see, nothing has changed from the Euclidean space that we had defined earlier. The only thing that is changed is the basis vectors. Okay. Now, if I have a point here, right, a point P here, then the projection of that point, right, would be orthographic projection over here and orthographic projection over here, right? It will give me, let me do this again, because that's not very visible, is it? This P vector here is going to be given by this orthographic projection here, which is going to give me alpha 1 and alpha 2 in the same way that in the Euclidean space, right, which is given by I and j here. If I have a point P and I project this orthographically, right, I get alpha 1 and alpha 2, right? Same thing. All right, so now back to what we were saying about a affine shape or affine equivalence. So you may remember from our last lecture that we said that the structure for motion solution, right, or the affine structure for motion solution, rather, is only defined up to an affine transformation defined by a matrix M, right, of 12 parameters. Remember that? Now, what that means is that there is a projection, one of these projections that we were talking about, right, that I can apply to my solution that is going to give me the exact same solution to my system of equations. And that's because when I define this space, I can use these two basis vectors, or I can use any other two basis vectors in that space, right, to define it. And any transformation between these two is indistinguishable. It equally defines my space. So if I have a mapping function phi from my set of points x to my set of points x, then, or psi, then this shape that I can call S, right? So let's say my shape is S. Then if I have psi of S equals some other shape S prime, S and S prime are affine equivalent, okay? So generally, an affine shape is going to be defined as the set S in X as the class of all affine equivalent point sets. There a question? No? Okay. So that just means that an affine shape for me is all the possible transformations, affine transformations I can apply to a set of points. Okay? So if I have a set of n points and I apply an affine transformation to it, that is still is considered the same shape. And if I apply another transformation, it's still the same shape. And if I apply all the possible transformations, that is my affine shape. Okay? In the Euclidean space, I can translate and rotate the shape and still the same shape. Here I can apply any affine transformation. There's a question in the back.
Based on what you said, can I conclude that there is no non-orthogonal coordinate system in the Euclidean space?
Yes, there is the orthogonal coordinate system, right? It's one of the possible coordinate systems I could have here. So I could actually have selected A1 prime here and A2 prime here, okay, such that these two vectors are not only orthogonal to one another, but that the vector A0, A1, or the norm of A0 to 1, is equal to the norm from A0 to A2 prime, which is equal to 1. If I had selected this would still define the affine space.
But my question is the opposite. May I have a non-orthogonal coordinate system in Euclidean space?
In Euclidean space, no. Euclidean space can only be defined by these orthonormal vectors, right? So the Euclidean space is a very particular case of the affine space. Very, very particular case. And in fact, we're going to use that fact to recover the Euclidean shape of an object. All right, and this is given, remember, because if I have a shape Q or a point Q or a matrix Q, and I multiply by that matrix, remember that transforms, I have my motion matrix Mi, transform it by this transformation Q, I get Mi prime that are equivalent, right? They're affine equivalent, these two. Okay. Now, let's see how we can use all this to recover the 3D shape of an object from multiple images of that object. And again, remember, we're considering only rigid objects at this point. Okay? All right. So there's a famous theorem that we're going to prove. It's called the Affine structure from motion theorem, I guess. That says given two affine views of four non-coplanar points, the affine shape of the scene or object is uniquely defined or determined. Okay. So I need two pictures of the same object under some affine transformation, obviously, these two pictures. And I need to define the object with at least 4 points. Okay? So let's see how we can prove that. We're going to do a visual proof. So I'm going to start with a three-dimensional object that looks like this. I'm going to find this point A, B, C. These are capital letters. Say that I have another point E in here, another one Q in here, and I'm going to define one more over here. Okay. I'm going to call this D. Okay. All right. Now I am going to project this onto two-dimensional planes, pi and pi prime, or actually pi prime and pi prime prime. So what I'm going to do, you see this triangle here defined by A, B, and C. Okay? That's exactly the same I have drawn here before. Let's call this pi. Right? This is the same as A0, A1, A2, right? In here, pi. This is triangle. So that defines a 2D space, subspace, in 3D space, right? And now we're going to project this. We're going to do an affine transformation onto two new planes. They are going to be, this is my marker here. This one is going to be parallel to pi, and this one orthogonal to pi. Okay? So, well, not quite orthogonal, at an angle. Okay. So if I do this, I'm going to obtain this thing here. Let's see if I can more or less. So this is going to be my point A. Let me call it A prime here. And my point B is going to be maybe somewhere here. And then my point C somewhere here. Okay, so B prime and C prime. Right? So I'm going to get this projection, right? You see how this works? Okay. And that's given by, or that triangle now defines this new plane here that I have called pi prime. And now if I project E onto here, it's going to be E prime right here, right? You agree? And if I project D, where is D going to be? Same place as E prime, right? So this is going to be equal to D prime too. All right, now let's do this at some angle here so that I get, maybe I'm going to do this. I'm going to do this projection, and then this projection, and this projection. So I'm going to get something like, looks like this. A, then B, and then C. Okay. And I'm going to call this A prime prime, B prime prime, C prime prime. And now I'm going to do the same for E. E is going to be here somewhere, E prime prime, and D prime prime. Excellent. Now, what we want to do is we want to consider, oh, I forgot Q, didn't I? Q projected here is going to be somewhere here, Q prime, and this one is going to be Q maybe here, right? Q prime prime. Okay, so far so good. Now we are given a, so this defines uniquely my three-dimensional space, right? Let's actually do this. This vector AB, AV vector here, right? And that other vector AC. These two vectors with A, say the origin, would define that pipeline, right? You agree? That's exactly what we have over there. And now if I have this vector, say, I have several options. I can either use AD here, right? Or I could use ED vector here, right? I could also use the ED vector here, you see, this one, which is the same because E, it's given us a linear combination of AB, AC. So I could also do it that way, right? So either way, I can define my three-dimensional space, right? OK. Now, I'm given a new point, P, whoops. I'm given a new point, P right here, OK? And I want to represent this new point in my affine space. So let's see how I can do that. Now, if I take pictures of that P is going to be P prime prime here, and it's going to be P is going to be equal P prime to Q prime, right? As before. OK. So now let's use barycentric coordinates to define my point P. So I'm going to start with AP vector. Now remember, A, I can consider it as my origin, right? So AP vector is going to be this vector from my origin to P right here. And what's this equal to? That's equal to, let's see. I could go, there are many options, but I could go from A to Q and from Q to P, right? OK, so I'm going to write AQ plus QP. Good. Now, AQ, I don't need to change because this is A, but QP I could probably also write it down as, you see, QP, this vector right here, it's exactly the same as this vector ED because they are parallel. You see that they are parallel, right? So these two vectors are the same up to scale, right? So I can actually write this as, this is the same as ED times a scalar, right? Now, what's ED? Let's look at ED, the ED vector. ED vector can be written by as AD minus AE. OK, so again, ED, this vector right here can be written as the vector AD minus the vector AE. That gives me that vector right here. Sure? Okay. What else? AE, this vector right here, is equal to, okay, it's equal to AB plus AC times some coefficients, right? Because that vector AE, this vector right here, is defined in this plane pi, and this plane pi is defined by the vectors AB and AC, right? So if I project this orthographically to these two vectors, I'm going to get my two coefficients, and these coefficients here, these alphas, are going to be equal, let's call this alpha E and, or let's call it alpha and beta. So I don't want to confuse. So let me call it alpha E and beta E. Okay, how about that? Now you see that this is parallel to this. Pi is parallel to pi prime. And therefore, the coefficients here, alpha E and beta E, are the same as E prime here, right? Alpha E prime, beta E prime. So I could also write primes here because they are exactly the same coefficients, right? Okay. Now, I could also write so let me go back. So I have AB and AC, and E is given by the coefficients that I have here and here, which are the same for this E prime, right? Establish this. But interestingly, they're also the same for D prime, right? Because in this projection, E prime is equal to D prime. So I could also write this is equal to alpha D prime or beta D prime. Well, okay, and how about, so that we have here for QP, which we have derived, but how about AQ that we have not yet? So I have AQ vector. What's this equal to, this AQ vector? AQ vector, let's see, where is AQ? A to Q right here is defined again by AB, AC. So I'm going to write AB plus AC as before. And now the coefficients here are going to be the coefficients of Q, which are the same as Q prime, right? So I could have alpha Q prime or alpha and beta Q prime. But these are also the same as P prime, right? So I could write either Q prime or P prime, same thing. So alpha P or Q and beta P or Q. All right, so let's put everything together. So I have AQ here and ED, and I can exchange it for these two here and get my final equation. So if I do this, I can extend this to, let's see, I have AQ, which is this thing right here. So I have alpha P prime times, sorry, I'm lost. There we go. AB vector plus beta P prime AV vector plus beta p prime AC vector plus lambda ED vector, right? And this, I can write it as alpha p prime minus lambda alpha d prime. This is d prime times AV vector plus beta p prime minus lambda beta d prime AC vector plus lambda AD vector. And from here, I can get my point P defined by the coordinates, right, the coefficients, alpha p prime minus lambda alpha d prime, comma, beta p prime minus lambda beta d prime, comma, lambda. That is my vector, right, in this affine space. Now let's see how we can reconstruct this then. So remember, we are looking for the three elements of P, right? Let's call them P1, P2, P3, or if you prefer, Px, Py, Pz, right? That's what we want, right? Now, we don't have that. What we have is two images that I have taken, right? Right? So this is an image that I take, a 2D image that I take with one camera, right? And this is an image that I take with the same camera translated and rotated in a different place, right? OK. So you have two images of the same three-dimensional object. Now, what do I need? I need AB, AC, and AD, right? AB and AC are the same as A prime, B prime vector. AC, this one here, it's the same as A prime, C prime, right? Vector. And the last one, which is AD, which is this one right here, can be given by A prime, D prime, right? Right here. So all of these correspond to the definition of my three-dimensional point. And what are the coefficients? Well, the coefficients are given by the corresponding images, right? So here, in my image, I know the coordinates of E prime, right? I mean, obviously I do. I mean, this is so I can take the coefficient of D prime, the coefficient of P prime, the coefficient of the other second coefficient of P prime, and the second coefficient of D prime. And with that, I can reconstruct P up to a scalar lambda, right? That's it. We just proved this theorem. We just proved that with two 2D images, I can recover the coordinates of a three-dimensional point in three-dimensional space. That's it. Pretty cool, huh? All right, so we've proven that this is possible. Now let's define the algorithm, right? We're going to define the first theoretical algorithm following the derivations that we have been using, and then the real algorithm that we're going to use. Okay? So we're going to find a couple of algorithms. And then finally, we're going to talk about how to recover the Euclidean shape, because remember, this is in an affine space, right? So this defines the affine shape, right? This shape is given by any arbitrary affine transformation. So it's going to look weird to us because obviously it's affine in affine space, right? Remember these shapes I showed you that were affine equivalent in the slides? We are going to recover one of them. We don't know which one. All right. So let's see our first algorithm for solving this, to solve this problem of recovering the 3D shape of an object or scene. Now remember from epipolar geometry, right? The affine equivalent of the epipolar constraint that we have here can be stated as follows. Let M be the projection matrix of the first camera. Now note that I'm saying the first camera. I could say the first image, right? It doesn't matter whether I have two cameras or I move the camera physically, right? It's the exact same problem. And M2 is the projection matrix of the second camera. Okay? Again, it could be the same camera after I have moved, translated, and rotated the camera. Same thing. Now, that means that I can get my image point, a small p, as M multiplied by capital P1 in homogeneous coordinates, where M, it's an affine transformation defined by my affine matrix A, which has to be non-singular, and my vector B. And that means nothing else than P, it's equal to AP, a capital P plus B, right? Now that's for the first camera. Now if I apply this the same with M prime, then I'm going to get P prime, and P prime is going to be equal to A prime P B prime, right? And that's my two equations, system of equations that I have. And therefore, I can write this in matrix form as A P minus B, right? I'm moving this to the other side and equaling this to 0, as always. A prime P prime minus B prime. And now this multiplies P negative 1. And this has to be equal to 0 and 0. Or actually just 0. Just write it as a 0. All right, so we want a non-trivial solution. Right? This is actually given by any solution for which the determinant of that matrix, right, A prime, P minus B, P prime minus B prime is 0. Which is the same as stating the following. Let's define these points P, small p and a small p prime as UV and UV primes, okay? As we have always done. Then we can write this in barycentric coordinates as U times its coefficient, let's call it alpha, plus beta V plus alpha prime U prime plus beta prime V prime plus some delta equals 0. Okay? And this is what we call the affine epipolar constraint, which is the same that we had derived before, but here in affine spaces. Okay? Now, that allows us to reformulate our famous equation with the fundamental matrix, where we have f, or our p vector in homogeneous coordinate uv1 times the fundamental matrix times u prime v prime 1 equals 0. And here, I'm going to change it for my new matrix, fundamental matrix, which I can define as alpha, beta, alpha prime, beta prime, my scalar, delta, and then just zeros everywhere else. Okay? So I parameterize my matrix like this, and I can call this now my affine fundamental matrix. All right. How are we doing? All right. I'm probably going to skip this. I think it's not important. So you can use the exact same algorithms that we have been working with here in the affine case for affine epipolar geometry and affine fundamental matrix, and you can solve. There's an algorithm that can extend this into recovering the 3D shape, but instead of doing that, why don't I go into the algorithm I really want you to learn, which uses a technique that you might be familiar with. Any guesses? All right, so we want to find an algorithm for a affine structure from motion. So let's see how this algorithm works. Now, as always, let capital PI's be our three-dimensional points, the world points in 3D space, and the small PI's, the corresponding image points, right? So we're going to have small PI's, or PIJ's maybe, the two-dimensional points. And I could say that I have, okay, let's see, what am I using? I'm using M for, okay, so I have P1J through, or actually PI1, small pi1 through pim, right? So I get the image point of capital Pi onto m different cameras. And I can write this in matrix form as follows. I have my pi1 through pim. Again, these are small p's. These are the image points. And this has to be equal to, remember that I have my matrix A1 through A. How many cameras did I say I have? M, okay. Times pi, capital Pi, this is a three-dimensional point, plus B1 through Bm, right? Translation vectors. Now imagine that I have eliminated the translation such that I can consider this irrelevant. And with this, let me call this vector right here, I'm going to call it Q sub I, right? Now, of course, this is a vector because these are the elements of my image points, right? Written in vector form. And this vector R, I have assumed that is not important. And now this one here, I'm going to call this matrix, which is a matrix of matrices, right? Call it capital A times PI. So I can write that QI equals API, right? So far, so good? Now consider that we have here these three-dimensional points, that we have endpoints. Okay. Then I have Q1, Q2, Q3, Q4, and so on. Let me call this my data matrix D, Q1 through Qn, the endpoints. And let's call P, capital P, the matrix of the corresponding three-dimensional points. Okay. And now I can write capital D, my Q's, is equal to this thing here, which is A, matrix A, times P, right? This matrix P. Yes? Did I lose anyone? What's that? Yeah, very good. We're going to get there in a second. Did I lose anyone before? Okay, are we good with this? Yep. Okay. Now, before we get there, let me ask you this. What is the rank of my matrix D? Now, let's review for a second. What is D? Anyone can tell me what D represents? The image points, right? Very good. This represents the image points. What does A represent? The transformation, the affine transformation that represents the camera projection, right? And what are capital P's? The actual three-dimensional points. Very good. Now, what is the rank of D? This is called usually the data matrix, because this is the data I do have, right? Of this equation, all I have is D. I don't have A or P, right? That's what I want to recover. I want to recover the three-dimensional points and the camera parameters, right? I want to know not only what the points look in 3D, I want to know X, Y, and Z, but I also want to know which camera took those points, right? To give me the small piece I do see. Wow, we already showed that that's possible, believe it or not. But now, what is the rank of D? Let's think about this. What is A? A is a matrix, right? Capital A, of matrices AIs, right? My cameras. Now, each AI is a, anyone can remember me? What is it? It's a matrix of what by what? 3 by 3 matrix. Very good, right? It's a 3 by 3 matrix. Excellent. So that means that this matrix is going to be 3m by 3. What is the rank of a 3m by 3 matrix, assuming the AIs are full rank? Because AI, remember, cannot be singular. Otherwise, you will not define an affine transformation. So what is the rank of A, capital A? At max, it's 3, right? So 3. So I know that the rank of A is 3. OK. Now, good. We're going somewhere. How about capital P, this matrix here? Where's the rank of capital P? P is, this is 3 by n, right? So what's the rank of a 3 by n matrix? At most, it's 3, right? All right. So that means that the rank of D is 3, right? right? Because D can only be constructed with the, I know that D is, so here, let's go back. D, which has these M points here, or these 3M coordinates, right, or 2M, and it's N, right? That makes sense, but it is constructed here by matrices of 3 by 3 and 3-dimensional vectors, right? And that's our limitation. So that means that I have here, what did we say? That was 3m by 3 times 3m by 3 by 3 times 3, this point here, right, or capital P rather, 3 times, what are we talking, n. Okay, excellent. Right? So because of this, the rank of A times P, right, can only be at max 3. Okay, now list the squares, right? So how are we going to solve this? Well, we're going to use our friend, linear list the squares. And D is given to us. So what is linear list of squares on D? It means to compute the eigenvectors and eigenvalues of D, right? The eigenvalue decomposition of our data matrix D. So let's do that, or singular values if you want. Same thing. So let's say eigenvectors, eigenvalues, or SVD. Let's say that we use SVD and we decompose D into U, W, V. Okay. So U is a matrix of singular vectors. V is another matrix of singular vectors. And W, it's a diagonal matrix of singular values. Right? Okay. So what I can do now, I can take only the first 3 eigenvectors or singular vectors here, and only the 3 ones here, right? And the reason I do this is because this matrix can only be of rank 3. Now, in reality, this matrix is probably going to be full rank, right? Because 2 reasons. First, my cameras are not pinhole cameras. Minor reason. But the real reason, my cameras are not Affine cameras, right? I can assure you they're not Affine. So obviously, D is probably going to be full rank, or at least larger than rank 3. But we know that theoretically, it can only be rank 3, right? And the least square solution tells me the 3 eigenvectors or singular vectors associated to this the largest singular values are the solution, the least square solution to that problem, right? So that's what I'm going to do. I'm going to keep the first 3 singular vectors on each side for U and V, and the corresponding singular values. And then I'm going to assign A, let's say A tilde. That's my recovered A, okay? So A tilde, because remember, D is equal to AP, and D is equal to U, W, V. So I'm going to assign this to U, the first 3 singular vectors. And P tilde, I'm going to assign it to the first 3 singular vectors of V. Now I still have W3, but W3 are scalars, right? They're just multipliers. You scale, it doesn't matter. Maybe I'll put them in A. You can also have them here. You can also have half of them here and half of them here. It really doesn't matter, right? Whichever solution you want. But that's it. This is insanely easy. Let's review. You have 2 cameras, or the same camera after a translational rotation, right? take two images of the same rigid object, create that D matrix, which is trivial, right? It's the matrix of point correspondences. I do have to have the point correspondences, right? And then once I have this data matrix, I do a single SVD decomposition or PC eigenvalue decomposition. And then I assign the singular vectors or eigenvectors into A and P, and I'm done, right? Well, almost done. This is a solution in the affine space. Now I want to recover the Euclidean solution, but I'm almost done, right? This is it. I mean, the algorithm couldn't be simpler. It's a few lines of code, you can recover the 3D shape of a scene or an object. It's insane, don't you think? I mean, you know, because I derived all the details on the board, that this is true, but it just should feel a little too easy, right? That it's that simple to recover the geometry, both the geometry of the object or the scene and all the parameters of the cameras, all the cameras. It's pretty cool. Okay. Now, of course, because I've used linear least squares, I should say that this approach that we have derived here minimizes the error defined by D minus AP squared, right? That's what the least square solution does. It minimizes this error, right? So that's what we have derived. All right, so now the question is, how am I going to go from this let's see if I can go back here. How am I going to go from this reconstruction to the actual Euclidean geometry? Now, remember that this is what's going to happen to me. I'm going to end up with one of these shapes in 3D. This is in 2D, but I'm going to end up with a shape in 3D. And it could be this shape, but that's not the shape I want. It could be this shape here. That's not the shape I want. This is the one I want, right? This is the Euclidean shape that I want to recover. And now I need to find a method that, given this, I can recover that. And how can I do this? Well, what's a transformation that transforms this shape into that shape? An affine transformation, right? So what I need to do is I need to find the affine transformation that transforms this shape into this one. And how am I going to do that? I'm going to have to add knowledge, okay? Because in the affine domain, I'm done. These three shapes are one and the same. They're affine equivalent. But if I know something about my world, and I do, orthonormality of the basis vectors, right? The matrix A, right? The matrix A for an affine transformation is non-singular. But for a Euclidean space is, anyone can remind me? I forget. What is A in the Euclidean space? It's a rotation matrix, right? It has to define a rotation. Can I use this knowledge to now find the affine transformation that guarantees me I have a rotation matrix for my cameras, right? The two or multiple M cameras that I have that allows me to reconstruct Euclidean geometry? Yes, the answer is yes. That's going to give me a system of nonlinear equations, but we know of a method called nonlinear least squares that I can use to recover this shape. And I have added the details that we covered in class of nonlinear least squares here somewhere in the slides. I think they're in the other slides. Yeah, here. There they are. So you have this in the slides that we covered the other day. You have all these methods implemented in MATLAB, the Gauss-Newton that we saw, the Marquardt method, it's something that's called regularized. Don't worry too much about this, but it just adds an identity matrix multiplied by a very small scalar that stabilizes the computations, makes it much more convenient, and much better to use in practice. All these methods, as I said, they're implemented in my lab. You don't have to implement them. And I'll see you Thursday.